lesson 5.1, I'm going to introduce you to the concept of antiderivatives, and then we're going to look at the relationship between derivatives, antiderivatives, and indefinite integrals. So derivatives tell us how quantities change, while the derivatives help us undo those changes. So it's like working in reverse. So to think of an example, you might think about when you square a value. Let's say 4 squared is 16, and then you take the square root, which brings us back to 4 again. And that's kind of like what we're going to look at with derivatives and antiderivatives. They undo each other, or they're working in reverse. And then that's where the indefinite integrals come in. They bring everything together in those two concepts together. Let's look at our learning objectives now. We have the first learning objective is to construct antiderivatives analytically. And then we're going to evaluate indefinite integrals using integration formulas and the method of substitution. Before we go into any examples, I want to go over some definitions for you and explain a couple things. So the first definition is the antiderivative or the integral. Now, what they're saying in this definition is kind of a mouthful, so let me just break it down for you in really simple terms. What this definition is stating, if we have a big F, so the function is called big F, and then we take the derivative of that big F, and we get little f. So little f is the derivative, big F is the original function. Now, that's what we've been learning so far, how to find the derivative of the big F. Now, if we want to work backwards, if we have the derivative, but we want to find out what the big F function is, that is what's called the antiderivative over the integral. And that is doing this in reverse. So that's what this is saying here. Now, we also have an explanation of what an indefinite integral means. So if we have a function that is big F, and we have infinitely many members of the family of the antiderivative of f of x. And I'll get to what that means in just a second here. The symbol for the antiderivative or the integral, that's this here that looks like a big, long, stretched out S. This is the function that we're trying to find the antiderivative of. This dx, in this class, we're just going to look at that to figure out what the variable is that we're going to be using, that we're going to be integrating in terms of. It means more than that, but we're not going to cover that and get into those details in this course. Okay, once we perform this operation, then what we get out is the antiderivative, which is the capital F, and then we have this arbitrary constant, and we usually call it plus c. Now let me explain to you what this means, because it's related to what we're talking about with the members of the family, the infinite many members of the family. So let's say I have this function. I'm going to list out a whole bunch of big F functions. So I'm going to label them as 1, 2, and 3. So let's say we have this big F function, x squared. Then we have another big F function, that's x squared plus 5. Then we have another big F function, that's x squared minus 100. Notice that if I take the derivative of each and every one of these, the derivative, no matter what, for all of these is going to be 2x. Even though the functions are different, notice that the constant is different. In F1, the constant is 0. In F2, the constant is 5. And in F3, the constant is a minus 100. So when we take the derivative of this, we get 2x. So there are so many different functions that we could take the derivative of and get the same derivative, even though the original function is different. And that is because when we find the derivative, any constants disappear. The derivative of a constant is 0. So that is why we add in this constant. We don't know what that original constant was because we're working backwards from the derivative. There is a way to figure out what that constant is, and we'll get into that a little later in the lesson. So these f's that I just put here that all have the same kind of function, but the constant changes, this is called our infinite family of antiderivatives, because there are so many different functions we could have with an infinite number of constants. So now let's look at our first example, which is probably the easiest one, which is integral of a constant. So this rule says, think of k as just some random constant, like it could be 5, it could be 7, it could be pi, who knows? It's just some constant. If we integrate a constant, and this tells me what the variable is going to be, we're going to represent this in terms of x. If I take the antiderivative, I'm going to get kx plus that arbitrary constant that we just talked about. So what I want you to think about is when we use the power rule, when we find the derivative, what we do is we take the power and bring it down in front and multiply it by the function, and then we take the exponent and we subtract 1. So now what we're going to do is we're going to work in reverse. Instead of multiplying and then subtracting 1, we're going to work backwards. We're going to add 1, and then we're going to divide. So when we use the power rule, when we're finding an antiderivative, we're going to add 1 and then divide by that same exponent. So our first example is find the integral of 4 dx. We can write this, even though we don't, we do have an x term in there. It's just that the exponent is 0. And we don't typically write that in there because x to the 0, as long as x isn't 0, this is just equal to 1. So we don't typically write that in there, just like we don't typically write 1x. We usually just write x. So for the purposes of understanding working backwards, I'm going to write in that x raised to the 0 power. So what we're going to do is we are going to add 1 to 0, which is 1, and then divide by 1. And so that's where we get the 4x from. If you want to go back and check it, if you take the derivative of 4x going this way, we get 4, so it works. And then, of course, we have to add in that arbitrary constant. So whatever this constant is, it could be an infinite number of constants. And that's what gives us our family of functions. Let's look at example 2. We have the integral of du. Again, we don't typically write certain things in because it just makes it easier. We don't normally write 1x, right? If there's a 1 there, we usually leave it out. That's what's going on here. It looks like there's no function there, but it's just 1 and then the du. So 1 is a constant, so we're going to use this rule here. So I'm going to rewrite it so that it's 1 du. The du tells me that u is my variable. So I'm going to take 1 times x to the 0. I'm going to take that 0 and add 1 to it, and then divide by 1. So now I have u to the first power over 1, which is just u. And then, of course, we add in our arbitrary constant. Let's look at example 2. We're going to look at power functions. That means we're going to be looking at something like x to the third, or x to the seventh, or x to the negative 5. Okay, we're going to have x raised to some exponent. Okay, I want to find the integral for part A of x to the third. So we have x to the third dx. Now we can use the reverse power rule for this because we're dealing with power functions. So the power function says I add 1 to the exponent, so my exponent will now be 4, and then we divide by that exponent, which would be 4. So that's where we apply the power rule. So we would get x to the 4th because we added 1, and then we divide by that same exponent. And then we add the arbitrary constant. So our final answer for the family of functions for the antiderivative is x to the 4th over 4 plus our constant. Now again, you can always go and check it and work backwards. So if I want to find the derivative of this, I should get x to the 3rd. So I bring the 4 down in front. If I'm taking the derivative, I know it's hard to switch gears like that, but it's going to take a little bit of time to get used to that. So we're going to bring the 4 down in front, and this becomes a 3. So I would have 4x to the 3rd over 4. The 4's would cancel, and when we take the derivative of a constant, it disappears. So working in the direction of taking the derivative, we get x to the 3rd. When we work in the direction of finding the antiderivative, we get x to the 4th over 4 plus c. Let's look at b. So we have the integral of x to the power of 2/3 dx. So we're going to add 1 to the 2/3. So that's going to give us 5/3 because we're going to add 2/3 and 3/3. That's going to give us 5/3. And so we'll have x to the 5/3, and then we divide by 5/3. When we divide by 5/3, instead of having two fractions or a complex fraction, we can do a flip and multiply, so we get 3/5 x to the 5/3. And then we add in our constant, so this will be our antiderivative. Okay, now let's look at example 3. We're going to talk about integrals that have the sum and difference of two functions, or it could be more than two. So if you think back when we first started derivatives, we had a rule that said if we had two functions that are added or subtracted, and we find the derivative, then it's going to be the derivative of each of those terms as long as the derivative exists. Now, we have a similar rule when we're dealing with integrals. As long as both of these functions you can get the antiderivative of those, you can split it up into pieces like this and do each of them separately. So let's look at example A. We have fx squared plus 8x minus 7x, minus 7 dx. Now we can split those into pieces and do each one separately. So when I find the antiderivative of 4x squared, that's a power function. So I'm going to use the reverse power function for the derivatives. So I'm going to add 1 to my exponent. So this is now going to become a 3. And then I divide by 3. And that's where this comes from. So that's the antiderivative of 4x squared. Now we have 8x dx. Using the reverse power rule, we have that we're going to add 1 to the exponent. So this is going to be x squared, and then we divide by 2. When we take 8 divided by 2, it simplifies to be 4, so we have 4x squared. Then we're going to subtract the integral of our constant, and this is going to be 7x. Because really, even though we don't write it in here, we have x to the 0, so we're going to add 1 and divide by 1, which will give us 7x. Now, something I want to mention about this c. When we find the integral separately like this, each one of these integrals is going to produce a constant. There's going to be a constant for each of these. So let's call it C1, C2, and C3. So when I find the integral of this, I'm going to get 4x to the third over 3 plus C1. Then when I find the integral of 8x, we're going to get 4x squared and then plus C2. And then this will give us 7x plus C3. Because all of those C's, C1, C2, C3, are all just arbitrary constants, we don't know what it is, we can just add them together as one and call it C. So we have just one arbitrary constant, and that is what we have right here. Let's look at part B. So we have 5x to the 2/3 minus 4 dx. So we're going to use, because this is a power function, we're going to use the reverse power function that we used for derivatives. So I'm going to add 1 to 2/3. So that's going to give me 5/3. And then I have to divide by 5/3, which I can flip and multiply so I don't have division of a fraction. So I would have 5x to the 2/3 times 3/5. And then this 4 is a constant, so we're just going to add on an x to it. So this is what we have right now. Now, because of this 5, and then the 5 that we get from finding the antiderivative, these two 5s will cancel, and I'm just going to be left with 3x to the 5/3 minus 4x plus our constant. Now we're going to look at integrating a function that's not a power function. We're going to look at the natural exponential function, so e to the x. If you recall, e to the x is kind of special because when we take the derivative of e to the x, we get e to the x. So when we're working in reverse, if we find the integral of e to the x, we get e to the x. So it's a little bit unusual, but we know it's true because we checked it in the lesson where we were working with natural exponential functions. And then, of course, you always have to add in your plus c. So we're going to find the integral of 3e to the x minus 5x dx. I want to point out that this is our natural exponential function, and this is our power function. It's x to some exponent. So keep that in mind and don't get these confused. So if I take the antiderivative of 3x, I carry the 3 down, and then the derivative of e to the x is e to the x. Then I'm going to subtract my antiderivative of this. So I have x squared and divide by 2 because I have to add 1 to the exponent. So that's where we get 5x squared over 2. The sign stays the same unless you get a double negative. And then we add in our arbitrary constant. Now we're going to talk about the reciprocal function. And the reciprocal function is 1 over x. Now, when we think about the reciprocal function, and we want to go to find the antiderivative, a lot of times our brains will go in the direction of wanting to use the power rule, because you can bring that x from downstairs upstairs by writing it as x to the negative 1. But unfortunately, what happens if we set it up like that and we use the power rule, we have x to the negative 1 over 1, And then when we use the power rule to find the antiderivative, I would have to add 1 to the -1, which would give me 0, and then divide by 0. And that's undefined, so we can't use that method. So that's why this is a special case. With all the other power functions, we can use the power rule. But with this one, we run into a problem. So we don't want to divide by 0. Now, if we think back to when we were learning derivatives, and we were talking about finding the derivative of the natural log of x, we had the rule that when we take the derivative of the natural log of x, we would get 1 over x. So if I work backwards, if I have the derivative of 1 over x and I want to find the antiderivative, that would be the natural log of x. So that's where this rule comes in. So be careful and not fall into the trap of thinking about using the power rule for this. So let's go through, now that we know the rule for the reciprocal function, let's go and find the antiderivatives involving this function. So in part A, we're going to find the antiderivative of 7 over x. If I think about pulling that 7 outside, because I can factor out any constants, then I would be left with 1 over x. So I would have, let me get my pointer, I would have 7, and then the integral of 1 over x dx. And now I know that 1 over x, that antiderivative, because we just talked about it, is the natural log of x. And now we bring the 7 down and we have that 7 in front. Now it's really important to put absolute values around the natural log, or I should say around the x for the natural log, unless we know for sure that they're all positive numbers. Because if you think back to your algebra class, the way that the graph of the natural log looks, there is no values in the domain for that function like 0 or negative. We cannot take the log of 0 or of a negative number. It doesn't exist, so that would be undefined. So we want to make sure that we put absolute value signs around that so that we don't run into that problem. And then, of course, we have to add in our plus c. Now here's an example of where it specifically tells us that the domain is greater than 0. So in this case, we're not going to have to worry about putting absolute values. Now, if you're unsure, put the absolute values in. Because if I take the absolute value of a positive x, that's still going to come out to the same answer if I don't put the absolute values in. So if you're in doubt, put the absolute values in, and then you don't have to worry about it. But in this case, since they're telling us that the x's are greater than 0, when we find the antiderivative, we'll be able to write it without the absolute values. So for this one here, we're going to just use the reverse of the exponential rule. And because e to the x is its own derivative, then working backwards, the antiderivative of e to the x is also e to the x. And of course, we're going to carry down that 6. Now, this is like saying 4 times 1 over x, and we just talked about it, that the antiderivative of 1 over x is the natural log of x. So we write this as the natural log of x, and we put the 4 in front. And now we have a constant that we need to take the antiderivative of. We have -1, and we know that when we have a constant, I just add the variable in front of it. So I have a -1x. And then, of course, we add in our arbitrary constant, c. Now, this is correct. However, because of this statement, we can also write it without the absolute values. Looking at example C, we have a polynomial divided by a monomial, and we're trying to find the antiderivative of this. A nice way to help make this easier is to make this and separate it into different fractions. So all of these terms are going to be separate, and you're just going to put x to the fourth over x plus 3x to the third over x plus 5 over x. Then, once you split this up, you can simplify it. So I can cross off an x on this first two terms here, an x on the top and the bottom here, and x on the top and the bottom here. And when we clean that up, we get x to the third plus 3x squared. There really isn't anything that we can do to simplify 5 over x, so that is just going to get carried down. Now, using the power rule, for the first two terms, we would find that the antiderivative is x to the fourth over 4, because we have to add 1 to the 3 and divide by that number, which is 4. The antiderivative of this means I'm going to add 1 to the 2, which gives me 3, and then divide by 3. And this 3 comes down here. And then this 3 and this 3 can cancel. And then we have plus 5 times the natural logarithm of x plus c. Now, in this question, it doesn't tell us that the values of x are going to be for sure positive. So we have to leave the absolute values in there. Now we're going to get into what do we do if we need to figure out what that value of c is. We need to know what that exact function is, and not necessarily the family of functions. So when we find an antiderivative and we get the arbitrary constant c, if we need to find that, then what we need is called an initial condition. And this initial condition gives specific information to help us find the exact antiderivative. So this is going to say, this is going to give us an example of where we have some kind of initial condition. So we're going to have a function and where the derivative is 3x squared minus 4x plus 2. We're also given another piece of information, and this is what is going to help us find that value of c. So we're going to integrate the derivatives to work backwards to find the antiderivative. And so we're going to set up our integral. Then when we integrate, we get 3x to the third over 3. And then for this one, we're going to get 4 times x squared over 2 because we're adding 1 to the exponent. And then because this is a constant, when we work backwards, we're going to get 2x. And then we add in that value of c. When we clean it up, this is what we're going to get. Now from here, this is where we're going to use the extra information to figure out what that value of c is. Since I know that this is now the function f of x, not the derivative, but the function, this is telling me if I plug in 1, I should get out 4. So now we have an x and a y value to plug in so that I can solve that for c, because that's the only variable that's left. So everywhere I see x, I'm going to plug in 1, and then I'm going to put 4 in for my output. So I have 4 is equal to 1 minus, this gives me 2, and then this gives me plus 2 plus c. And all we have to do now is solve for c. So we're going to subtract everything from both sides. And we're going to get that c is equal to 3. So now we know what our constant is. And it's because we were given this extra information that we can use to figure it out. So our final answer is, or our exact antiderivative is, x to the third minus 2x squared plus 2x plus 3. in example 7, we're going to work through an application. Something that I want to bring to your attention is in this application, we're going to be working with the derivatives and the antiderivatives. And sometimes when you're new at doing this, if you've never seen it before, it's going to get confusing and you might lose your bearings in your mind of which direction you're working in. Am I, working towards finding the derivative or working towards finding the antiderivative? Sometimes that can definitely get confusing, and it happens to me still today. I just have to refocus. So if that happens to you, don't worry, that's normal. So let's see. The problem says we have a marginal cost function, and we know it's marginal because the cost function is c, and we have a prime here. And when we take the derivative of the cost function, we have the marginal cost function. And that is negative 0.04x plus 26. X represents the level of production, meaning X is going to be the number of items that are produced. And then C prime is going to be the marginal cost. And we're going to try to find the cost function, C of X. And then we're going to use this information as well here too. The problem tells us that when they produce 150 items, the cost is known to be $6,555. So this is information that we can use for our initial condition. It says we have 150 items. And remember, X was the number of items. So if we write this in terms of coordinates, we have 150 as X. Then it says that the cost function is known to be 6,555. So that's our output. So we have our X and our C of X now. And we have a point that we can use to find our exact cost function. So we have 4 parts to this question. First, we need to find the marginal cost when the items produced is 530. Then, in part B, we need to use the marginal cost function to find the cost function. And then once we find the cost function, we're going to evaluate it at 530. And then we're going to interpret what these both mean. So let's work on part A here. So in part A, we needed to evaluate the marginal cost function at 530. So when we plug in 530 into the derivative, and we multiply and complete our order of operations, we get 4.8. For part B, we needed to work backwards to find the cost function, and we're going to integrate the marginal cost. So here's our marginal cost. This is a power function, so I can use the reverse power function rule. And then this is a constant, so I know that's just X. And then, of course, we add in the arbitrary constant. So when we simplify this, we get negative 0.02x squared plus 26x plus our constant. Now, to find the exact value of C, we're going to use that initial condition that was given to us in the problem, and we're going to plug 150 in for the X. And for the cost function, we're going to put in a 6,555. And then we're going to work that out and solve it for C, and we get that C is 3,105. So the exact cost function is going to be negative 0.02x squared plus 26x plus 3,105. So in part C, we were asked to find the value of the cost when 530 items were produced. So this is where you have to be careful. This is C without the prime. This is the cost function. So we want to make sure that we're plugging that 530 into the correct function. So when we plug in 530 in for X into the cost function that we just found, we get $11,267. Now, in the last part, part D, we need to interpret what these values mean. So we found the marginal cost at 530, that was part A, and now we found that cost at 530 in part C, so that's what we're gonna interpret. When we plug in 530 into the marginal cost, remember this is the instantaneous rate of change on the cost function when X is equal to 530. This also represents the slope of the tangent line at that point. And we have talked about how we can approximate the marginal cost by using that tangent line. So this 4.8 that we got when we evaluated that marginal cost function, that means if we produce 531 items after we already produced 530, we could estimate using the slope of the tangent line that to produce one more item, that's from 530 to 531, that cost would be $4.80. And remember, this is only approximate. If you want the exact cost, you have to plug 530 and 531 into the cost function and then find the difference. Now, when we evaluate the cost function at 530, that's going to give us the actual cost. So that's what we found here. So that is the amount of money that it's going to cost for producing 530 units. All right, let's sum up all the major points of this lesson. The first one that I want to remind you of is that the antiderivative of f of x is written like this. Okay, this is your integral, which represents, we're going to find the antiderivative. That's the notation you're going to use. And this dx reminds you that we're doing this with respect to x. I've emphasized this a lot during the lesson, but let me mention it again now because this is really key. Antiderivatives are the reverse process of differentiation. If it does not have specific limits of integration, then that's why we call it the indefinite integral. And actually, I'm not sure if I brought that up. Later on, we're going to talk about the definite integral, where we're going to have what's called limits of integration, where you would see a lower limit down here at the bottom of the integral symbol, and then we're going to have an upper limit over the top part of the integral. And when we have those numbers there, that means we're going to evaluate it over a specific interval. That's the definite integral. Now, when they don't have limits here, lower and upper limits, then that's called the indefinite integral. And the indefinite integral represents a family of functions, and that's when we have the plus c. Since we have that plus c, we could plug in any constant we want, and we would have so many different functions. But they're all the same, they're just going to be shifted up or shifted down. When finding the antiderivatives, we add a constant c to account for all possible functions that have the same derivative. And that's what I talked about at the beginning. You could have x squared plus 1. You could have x squared minus 5. You could put any constant at the end of that. And when you take the derivative of those, you're going to get the same derivative because that constant is going to disappear.